Now we'll discuss about the water system. Now we'll discuss about the water system. Okay, this is our water systems. Here in the phase diagram, we are in a position to describe the water system. It's the one component system. It's the one component system. Inside the heading of one component system, we will describe two things. One is the water systems and the other is the sulfur system. Let's take the graph very carefully. So here in the x-axis we are putting temperature and in the y-axis we are putting pressure. So how to interpret the graphs? Let's take the example. Here pressure and temperature. If I am putting this line, that means here pressure is directly proportional to the temperatures, because if increasing the pressure, temperature is also increasing. If increasing the temperature, pressure is also increasing. If increasing the pressure, temperature is also increasing. That means for this graph, both pressure and temperature is increasing simultaneously. So in this case, pressure is directly proportional to the temperature. Takes another example. This is pressure and temperature. If I am putting this line, that means whatever may be the temperature, whatever may be the temperature, pressure is not increasing. So in this case, pressure is constant. Pressure is constant. Similarly, we can take another example. Here pressure and temperature. We will put this graph like this. That means whatever may be the pressure, temperature is not increasing. That means here temperature is constant. We can say temperature is constant. So three things we explained in the graph. Here pressure is directly proportional to the temperature, and here our pressure is constant, temperature increasing, and here temperature is constant and pressure is increasing. We'll put this concept while illustrating the water systems. In the water system, water is present in three states. In the area AOC, it is present in solid state, that is ice. In the area AOB, water is present in liquid state, water in liquid state. And in the area BOC, water is present in the vapor state. So we can say water gaseous. So let's explain the curve. Okay. Suppose if we are thinking about the OB curve, what you are visualizing here? Here we are visualizing with the increase of pressure, temperature is increasing. With the increase of temperature, pressure is increasing. So in this curve OB, here pressure is directly proportional to the temperature, which is in accordance with the Gay-Lussac's law. But if we will see the OA curve, what you are visualizing, with the increase of pressure, temperature is decreasing. With the decreasing pressure, temperature is increasing. With the decrease of pressure, temperature is increasing. That means for this AO curves, for this AO line, pressure is inversely proportional to the temperature, which is not in accordance with the Gay-Lussac's law. It is very surprising. Why? Always Gay-Lussac's law is followed, but when we are discussing about the OA curve, this is not in accordance with the Gay-Lussac's law. Why it is happening so? Pressure is not directly proportional to temperature in the case of OA. The point is that this is due to the increased volume of ice. Suppose ice is being formed from liquid water. At the time its density becomes high. Why? Because due to the formation of cage-like structures, when liquid water molecules come in close with each other in the solid state, they form a cage-like structure, CAGE, cage-like structure. Due to this cage-like structure formations inside the solid ice, the volume of ice becomes more. The volume of ice becomes more. This is not an ordinary case. For instance, you take one cylinder. Here, for instance, 10 liter of gaseous molecules are there. Gaseous molecules are there. They are far apart. When I increase the pressure to almost 1 liter, what happens? The gaseous molecules comes close to each other and the van der Waals force of attraction increases between the molecules and it may convert to liquid state. So what we see, if we increase the pressure, the volume, if we increase the volume decreases. So there is a what we are interpreting from this scenario, that is, if we increase the pressure, gaseous states converted to liquid state, and if we increase the pressure, liquid state may convert to the solid state. But in this case the scenario is different. For instance, this is the point, transition point. Here, left side water is in the form of solid, ice is present. The right side liquid water is present. So in this condition, is a transition phase. In this here, the solid water is being converted, ice is being converted to liquid. Suppose now it is in 1 atmospheric pressure. If I am now increasing, if I am increasing the pressure, what we are observing, if increasing the pressure by keeping the temperature constant, we are observing water is converted to liquid. But in other situation, this is not obeyed. In other situation, when we increase the pressure, gas converted to liquid, liquid converted to solid. But here, if you are increasing the pressure, you are observing solid is being converted to liquid. This is the anomalous behavior of water, because the volume of ice becomes more than the volume of liquid water. So this type of anomalous behavior is seen in water. So in this case, what we are observing, pressure and temperature are inversely related. So this curve is called the fusion curve. This curve is called the fusion curve, because here fusion takes place, solid is being converted to liquid. This is called in this curve, the water in its liquid state is being converted to water in vapor state. So this is the transition curve. In this curve is called vapor pressure curve. This curve is called vapor pressure curve. And here in OC curve, in the left water is in the form of ice, in the right it is in the form of vapor. So here in this condition, water from solid state is directly converted to water in vapor state. So this is the conversion from solid to gas. This is called sublimation. Sublimation curve. In our day-to-day life, we have seen naphthalene bulb, what we call in Hindi Karpura Gauram Karunavataram. So here this is the naphthalene ball, the two benzene ring. This is naphthalene ball. When we keep naphthalene in our pocket, in our bag, for putting clothes, after some days we visualize that most of the naphthalene is not there, because from the naphthalene ball undergoes sublimations and it becomes vapor, it becomes gas. So this is the one example. Naphthalene is the example where sublimation takes place. Similarly, OC curve represents the sublimation curve. OC curve represent the sublimation curve. So, and this OD is the metastable curve. This is called metastable curve. OD is the metastable curve, and O is the triple point here. O is the triple point here. In this O, three states of water coexist in a single point, that is 4.58 mm of mercury, and the temperature is 0.0075 degrees centigrade. 0.0075 degrees centigrade. So this for the attainment of the triple point for water, some particular situation is required, that is 4.58 mm of mercury and 0.0075 degrees centigrade. If we will fluctuate little bit from this specific conditions, attainment of triple point is not possible. This is the simple illustration of the phase diagram for the water system. In the next class, we will calculate the degree of freedom for this OA, OB, OC, OD curve, and the area AOC, AOB, and BOC. Okay.